Hello, welcome to session number 6 in the series Digital Multimedia Processing. Earlier in the series, we have been doing a photometric correction or photometric variation of a pixel, where the pixel value depended only to the pixel in the original image. It didn't have to do anything with the neighbor. So in previous session, we briefly discussed, right? We briefly discussed about just one second. So we briefly discussed about how to do region-based processing, right? So if I have an image, right, with a certain width and height, so what will happen is I start with the first pixel right in this corner, right? So let's mark it like this. So what we were talking was we process the value of that pixel based on its neighbors, and let's say these neighbors are over here. They are basically 3 neighbors, for example, or it can be only two neighbors. It can be 4 neighbors. It can be, so it can be 4 by 4, 3 by 3, right? 5 by 5. Usually it's an odd number because we want to investigate a middle pixel, in the sense that in row and column it is at the middle, right? So if it is 3, then you have 1 pixel on the left, 1 pixel on the right, 1 on the top, 1 on the bottom, and then the diagonal elements. Now let's say if it's a 5 pixel, right? So now what do you have? You have got these, right? So now you are talking about 5 by 5, right? So you're talking about a 5 by 5 neighborhood for a pixel to determine the value of the pixel, right? So now for this purposes, you might have to what is called padding the image. So for example, if I want to apply a 5 by 5 kernel to determine the value of a pixel, then I have to pad it with a I have to pad it with a 2 pixel boundary, right? With a 2 pixel boundary. Now the same thing I have to do over here also, right? So here also there will be a 2 pixel boundary here, right? So this is referred to as padding, right? Okay, so I want to do a padding of the image, right? And once the processing is done, I would have to take these pads off, right? So that will be called depadding, right? So the first procedure in this whole exercise would be to pad the image and to depad the image. So what I'm going to do is I'm going to write a program for padding and depadding. Now let's say the middle value of a pixel. So what are we going to discuss? We are going to discuss averaging. Okay, in averaging, what do you do? The middle pixel value depends on the average of all the pixels in the kernel. So for example, if I have, let's say, a image which is something like this, these are the numbers, let's say. Okay, let's say these are my numbers. Okay, so let's say these are my numbers for so if I take this value and replace it by the average of all the values, so my kernel would be a matrix multiplication member wise with this matrix, right? So if I multiply member wise this matrix, so let's say this is A and this is my kernel, so I would have to do A into kernel, right? So now that will give me the member wise multiplication of the matrices. Then I have to divide it by 9 because there are 9 elements, so that will be the averaging, right? So this is one way of doing filtering, which is also known as averaging, is a form of a low pass filtering, right? So this is a low pass filtering. Okay, now I can perform same thing by doing something like I can find a median, right? So median is also a form of a low pass filtering. So what I can do is I can take 210, for example, 190, 67, 193, 182, 29, 56, 44 and 33, and then I sort it out as in the increasing order. I can say 33, so 29 goes above that, so 29 is done, 33 is done, sorry about that. Then we have got 44, right? So this is 44. Then we have got 56. Okay, then we have got 63. Okay, then we have got after 63 we have got 182. Okay, then we have got 193, right? Then sorry, we have 190, and then we have 193, and then I have 210. So now it is sorry about that. Now it is basically in a increasing order. So now this is in a increasing order. Now I can find out the mid value. So I'll take the fifth element, which is the mid value, which is 63. So I will replace the center by 63. So 182 is replaced by 63, right? So this form of filtering would be known as median filtering. Now sorry about that. Now we can also do what is known as a high pass filtering. Okay, so in case of a high pass filtering, what can we do is we can choose a kernel which is like 8 minus 1 minus 1 minus 1 minus 1 minus 1 minus 1 minus 1. Now if I do this, what's going to happen in my high pass image is I'm going to have a gradient, right? So here I don't have to do 1 by 9, because if I see the sum, the norm of this whole entire matrix is going to be 8 elements of minus 1. So 8 minus 8 is going to be 0. So the image is going to be having no DC value to it. Now if I was to do the same filtering with something like that, okay, so in this case what is going to happen is I'm going to get the original image, right, and then gradients will be added to it, right? So what I would have is 9 minus 8 kind of stuff, so that will be 1, right? So you understand that this would be a gradient plus the center pixel, right? So it will be gradient, so the pixel value plus the gradient, pixel value plus the gradient. Okay, so that will happen. Now the same thing is there with, so this would be called a high pass filtering. Now there is another matrix or kernel which is called Laplacian. So in Laplacian is just like a hat actually. So sorry, Gaussian is like a hat. So in Laplacian what you have, you can have 1 and you can have the nearest neighbors as minus 1 and the diagonal neighbors is 0. So in this case again it will be 4 minus 4, so it will be around DC value. Only gradients will be there. Now I can do the same thing with something like 0 minus 1 0 minus 1 5 minus 1 0 minus 1. Here we have got the original value plus the gradient. So in that case again this would be a high pass filtering. Okay, another thing is we can use what is called Robert Sobel, right? So we have got different filters for edge detection, so they are called Robert, Sobel, Prewitt. Okay, so these are for edge detection. Now we know that when we traverse across the image, we can traverse this way, we can traverse this way. So the gradient can be established this way along the width, or the gradient can be established along the height. Now you can also establish a cross gradient, right? So in that cross gradient you are going to use something called a Robert, which is a 2 by 2 kernel. And the Robert filter, which is a 2 by 2, it is of this form, minus 1 0 0 1. So this is like a cross edge detection. So basically if you proceed this filter along this or along this, you will be basically enhancing the edges in both x and y. So basically you will be enhancing edges in this direction. So that will be called the Robert filter. Now in case of Sobel, right, we have 2 filters running for 2 edge enhancements. So one would be for the width, other will be for the height, right? So for width, okay, the kernel would be the kernel would be -1, -2, -1, 0, 0, 0, 1, 2, 1. So now this is going to give you some form of a edge detection along the when we move along the width. So it will always give you all the vertical edges, right? Now for if I was to go for height, right, we have a different kernel. Okay, and that kernel is going to be -1, -2, -1, 0, 0, 0 is just a transpose, right? So this will be 1, 2, 1. So I have got two kernels for the Sobel filter. Same thing is for the Prewitt filter. Okay, so in this case I am going to have for vertical, so this one is for the horizontal edges, right? So now for vertical edges I have over here these, right? And then I have got another one which for the horizontal edges, which is going to be this, right? So this is what we're going to have. So these are the most common ones which are used. Then they are going to be 5 by 5. You can do a Gaussian, which will be approximation of a hat function, right? So you can do a kernel for various forms of filtering. So now in this whole entire process, you have to do this. You have to take an image, you have to pad that image, then you have to do apply the filter, then you have to depad the image. Okay, so this is the procedure which we have to follow when we write the program. So we are going to have a separate function, one for this, one for this, one for this. Now this is referred to as convolution, right? So what you are doing is you are taking a kernel and you are moving it on the image. Okay, so this is for example my kernel, and I'm going to move along this direction, right? Or I'm going to move along this direction. So I'm moving the kernel along with the signal, right? So this would be referred as convolution. So in this case I'm going to write a method for convolution. So this will be using convolution method, right? So this is what we are going to do in this session, right? So there will be three codes, three functions. One is for padding, depadding, and the other one is going to be for convolution. In convolution I will do three variants. One will be for median, other is for your low pass, and the other one is for the regular, high pass and edge detection. So I'm going to do three functions for convolution, right? So let's get started writing the code, right? Okay, so now we are ready to proceed, right? Just one thing I want to check. Hello, yeah, so I'm perfectly fine, audible. Okay, so let's go ahead and write a code, okay, for padding the image. So I will write it under here, and this would be a void, and it is going to be called pad image, and it is going to receive a character, a pointer to a string, right? And that I will call as fpath, and then I am going to have a character stream which will be pointing to the right path, and then I will give it a unsigned int as the pad value, right? So here I can get started. So first of all I'm going to create two file pointers. One is for reading the image, the other one is going to be for writing the image, right? And then I am going to declare a character, unsigned character ch, and then zr will be the 0, right? So two characters I will create. So this is case sensitive, so I'm going to do that. And then you have a unsigned integer it. I'm not sure why I'll be using that. Just one second. width and height would be there, right? Okay, so this is for writing the header. In header I have got number of integers, right? And also I would have short, right? Unsigned short, sign short st, right? So then I would have unsigned integers, like you want to have the width, the height, the offset, right? And I will have two more. One is going to be the enhanced width, enhanced height, right? So we have that. Now first thing is I'm going to open the file for reading, so that will be f open. Okay, the path is pointed by f path, and then I am going to open this in a binary mode for reading, right? And first thing I'm going to check is if fp is a null pointer. If fp is a null pointer, then I am going to write to myself a message, printf failed to open the input file, correct? And then I would just say return from the function call. Okay, otherwise we have succeeded in opening the file, right? So the next thing which I'm going to do is I'm going to read the header, right? And I'm going to write a header, right? So I'm going to say fseek, okay, the offset, the width and the height. So I will read the offset of a file which is fp, which is at 10th byte in the header, right from the starting. So I'm going to say f read, and there, that is, I'm going to read that in offset, right? So I am going to read that in offset, so I have to pass a pointer to that. Okay, and it will be having a size of integer, right? And 1, and from the stream fp, so that would read the offset of the data offset from the start of the file. Then I'm going to see whether I have to read the 18th byte, which is going to tell me about the width of the image. So I can say width of the image will be given by this f read, right, from that stream. And then also I want to read the height of the image. Okay, so the height of the image, okay, is the next succeeding integer, which I'm going to read here from the stream. So once I have done that, my new height would be the pad size, right? The new height would be the pad size, right? So in this case the width is going to have padding on the left as well as right, so then the new width will be twice of pad, okay, and the new height would be height plus twice of pad, right? So once I have that, I am going to open the file for writing. So I'm going to say fw is equal to f open, then the path is the w path, right, comma, in a write mode in binary, right? So once I have done that, I'm going to check if fw is not null. If it is null, that means I have failed in opening the write file. So I'll just print myself a message, printf, then I'm going to say is failed to open the output file, right? And that I am going to say is I'm going to close first the open file, right, and then I'm going to return. Okay, so this is what's going to happen if I fail to open the output file, else I'm ready to write. Okay, so first thing is I'm going to write the header. So I'm going to place the the pointer fp to be at the start of the image, right? Okay, so once I have done that, I have to write 2 characters, right? 2 characters I have to write. So I will say fread character from the file, size of character 1, and then you are going to say fp. So reading from the f path. Then I'm going to write fwrite, right? And then I'm going to write back the same character which I have read, size of character, right? 1 character to fw. So I have copied 1 character which will be b. Okay, so this will be copying b. Okay, now the next one will be, so here I'm writing the first byte which is called b, and this is going to be 1 byte. Okay, here I am going to be writing m, that will be the second byte, correct? Okay, so once I have done that, I'm going to find out the size of the file, right? So how do I find the size of the file? It will be it would be equal to wn into hn plus, okay, into 3 because there are 3 colors, right? 3 colors plus the offset. Okay, so this will be the new size of the file. So I have to write this new size of the file, right? So first of all, I have to advance the read pointer. So I'm going to say fread. Okay, I am going to waste the red value, size of integer, right, 1, and from fp. Okay, so I have read, so I have advanced the pointer by 1. Now instead of writing what I have read, I have modified it to reflect the new size of the image, and I'm going to say fwrite ampersand it comma size of integer, right, comma 1 comma fw, right? So here I have written 4 bytes, that will be the file size. So I'm writing here file size. So now we are at the 6th byte, 4 plus 2 at the top, right? Then I am going to say is fread, I'm going to read the reserved value, right? Fread the reserved integer, and I'm just going to write as is, right? So I can just copy that, so I don't have to type again. So I can just copy this one, right? So I have advanced the pointer by 1, and then I write it, Control C, Control V. So once I do that, I have written the reserved word which is having a value of 0. So reserved word, and I have proceeded to 10th byte, right? Next is I am going to write the offset. So the offset is also going to remain the same, right? So I am going to read the offset and write. Okay, so I'm writing the integer at 10th location to be the same. So what I have written here is going to be data offset, and I have advanced to byte number 14 now, right? Next I am going to do the same stuff. So now I have to write, so I have to write the what you call the header size, right? So after this I have to write the header size. So I'm going to just repeat it, and at this point I have written the header size. Okay, so the header size is 40 and I have advanced to 18. Now I have reached the width of the file, so I'm going to just do fread, okay, so as to advance the pointer, right? And then I am going to fwrite something else, right? So I have advanced the pointer, and I am going to do a fwrite, which will be the new width of the file, right? New width of the image. So I'm going to write here this one as the new width of the image, correct? So I have written the new width. Okay, and I have proceeded up to 22. Okay, so the next one I'm going to do is I'm going to advance the pointer, right? And here I'm going to write a new height. So I have written the new height of the, okay, so I have written the new height. Okay, and the new height is now has advanced the pointer to 24, 26, isn't it? Okay, so it has advanced the pointer to 26. Next, I'm going to just write the number of planes, which is going to be a short, right? So after width and height, I have to read a short. Okay, so I have to do a f read ampersand ht size of short, which is going to be 2 bytes, right? 1 fp. Okay, so I have advanced the pointer by 2 bytes. Okay, and then I'm going to write the same stuff, f write ampersand st size of short, 1 short, and fw. So here I have written the what you call the number of planes. Okay, then I will read another short, which is bits per pixel, right, which is going to be 24. So I'm going to write here. So I have reached so at this point I have reached 2, right? So it will be 28. So at this point I have read the number of pixels, okay, number of pixels per number of bits per pixel, right, per pixel. Okay, so here I have advanced the pointer to 30, right? So now we have got a few more integers to write. The next one is the compression, which will be an int, right? So I will just copy this one, Control C, Control V. So at this point I have basically read the compression. Okay, so I have reached at this point. Just 1 second. Okay, so I have written up, let me just check if everything is okay. Okay, so I have written up to compression, few more bytes to write, which will be just a copy, right? So I'm just going to write few more bytes. So this one is going to be after compression we have got what is called the image size, which is at the, so the compression has left me to 34th byte, right? So I'm next thing which I read is a 34 byte. Now here I'm going to write the size of the image. So the new size of the image would be into 3, right? So this will be the new size of the image, right? So I will say here image size. So that's what I have written, and here I have proceeded to 38th byte, right? Okay, the next one would be the X scale, which will be the width scaling. So this will be width scale, and here I have reached up to 42, right? And then the next one will be the height scale, and then I have reached up to 46, right? Then I am going to have number of colors, right? That's another integer, right? Okay, so number of colors is another integer. So let me just write that. So this will be number of colors. Okay, and then if I write one more, that will be number of important colors. Okay, so once we are done with that, we are ready to deal with the data. Okay, so first thing is I'm going to for the pad, the number of pixels of the pad, I'm going to write 2 rows, right? 2 rows going to write a new image, right? So I'm going to say for unsigned int I equal to 0 and I less than pad, and then say I plus plus, right? So I am going to basically write the 2 rows, and what will be the width of the rows? The width of the rows will be unsigned int j equal to 0, j less than wn, right? And j plus plus. So this is the 2 rows I am going to write, right? So let me just add this here. Okay, and this will go in. Okay, so I'm going to write here 3 values for blue, green, red as 0, right? So here I have not read anything from the original image, so I'm going to say fwrite, and I'm going to write 0 size of byte or character, size of character 1 character to fw, right? So I will write this 3 times for the 3 colors to have a black representation for black. Okay, so this is my 2 widths which I have written. Now I am ready to go for the writing the data, right? Right, so now I am going to, okay, so we have reached to a point where we are going to read the image data and write it. So let me just put here some more numbers so that we know we are at the right half set here. Okay, so now here I'm going to say for unsigned int I is equal to 0, I less than the height I plus plus, right? And then, so of course, you know, this came over here, this should be here, right? So here I am going to write the first first pixels which will be equivalent to the pad, right? So I can say I can copy this stuff, right? And over here I can paste that, and here I need to just write it as much as the pad size is there, right? So I have read and written the first column, which is going to be 0 because it's padded, and then the actual image, right? So then I have to write another for loop for unsigned int j equal to 0, j less than the width of the image, right? Width of the image j plus plus, and here, sorry about that, okay, and here I need to read the data from the image and write it, right? So I have to do it for 3 colors, right? So I have to say fread, read the byte, okay, read the byte, right, 1 byte at a time, and then I have to write the same stuff, fwrite, same character which I have read. So this is the actual data of the image, right? So here I shouldn't go up because then the image will not come out right. Okay, so I have written the blue of the original image for a particular row, then I have written the green, and then I have written the red. So once I have done that, then I have to add the pad, right, where I have to write the zeros, right? Okay, so Control C, Control V. Okay, so this way I have written one row, and then I will go to the next row and the next row and so on, right? So once I have written all the rows, right, I have to basically write the two rows which are going to be the height of a pad and the width of Wn. So over here I have to repeat the whole thing again. Okay, so at the end of this I would have written the entire padded image. Then I have to just say flush, okay, fw. Then I'm going to say fclose, fp, and then I'm going to say fclose fw, fclose fw. Okay, so now this would be the else of the right, so let me just check. Yeah, this is the else of the right. Okay, so now I have written the function to pad an image. So let's generate the prototype for this one in its header file, so which is over here. So that's the prototype, and in a prototype I don't need these names, right? So once we are done with this prototype, then I can go to the main program, and here I want to call that function. Okay, so pad image. So I'm going to pass here the input file, which is that. Then I have to write for the output file and then the pad. Now something about a note about the padding. For some reason BMP are going to pad it with the even number values. So let's say with 2 or 4 or 6 or 8 or 10, you know, that's the limit. Now the another thing which I have to do is I have to create the path for the output file. So that's the path for the output file. I will call this as a padded path or pad path, and this I will call padded.bmp. Okay, so let me see if I'm recording. Yes, I'm recording. So I have created this pad path, which I'm going to pass to the input, or to this function, argument to this function. So I'm done with this, and let's say we do this with Lena. Okay, and I also want to make sure that my output folder is empty. Okay, so I'm just going to delete this. So output folder is empty. So I'm going to see if I can get the Lena to be padded. So now if you see here, there is no padding on this picture, right? Now I'm going to run this routine. So I'm going to say build solution. Okay, and then I'm going to say debug. So it's written. So I'm going to go and check if it has written the padded path. For some reasons I have done some mistake here. That's why I'm not even able to see it. So let me just fix this issue. Right, let me just fix this issue, and after that we can see the results. So I'm going to put you on a pause to debug it. Okay, so what I was doing was I just copy pasted. So I copy pasted this again here. So my header was messed up. So I corrected that. Now I'm ready to run this. So I'm going to build the solution. Right. So that's building the solution. Then my folder is empty here. Right. This is my output folder. So I'm going to say debug start without debugging. And I have written the file. So I'm going to go here and check. And that's written file. So I'm just going to open it. So now you see here this one and this one. Okay, so this one is basically padded one. So I have padded some 0 pixels around the image. So now this image is ready for the input to the filters. So right now there are 2 pixels padding, right? So if I look at here, and if I look at here, so this is a 2 pixel padding which I have done, right? So this is a 2 pixel padding I have done. I can do any pixel padding, but I have to make sure that they are even numbers. So for example, I can go here, when I call this, I can pad it by 50. Okay, and I can build solution, and I can start without debugging, and it's done. And if I look at the output, okay, under processed, I have an image which is padded by 50 pixels, right? So this image is padded by 50 pixels compared to the original image, which is over here. So this is how the padding is done, right? Now I have to do the reverse of this. So I have to write a code for depadding the image. Okay, so let's go ahead and do that. So what's going to happen is most of the function is going to be the same, right? So if I go to image write.c, the same header I have to write, right? So what I'll do is I will write a new function over here, and I would say void, and I will say depad img. I'm going to receive a character which will be an input path, then character string referring to the right path. Okay, and then I'm going to have a int for padding, so that will be a pad. Okay, so once we are done with this, I'm going to copy the entire thing as is of this function. So I'm going to go from here up to here, Control C, Control V. Okay, so I've just copied the same procedure, but here I'm going to modify this. Now whatever is the pad value which I have written, I have to depad, so it will be minus, right? And then the header writing is going to be as is, and after that this is going to change. So from here onwards I can say up to here, right? So I'm just going to delete this. So up to here, right, I have just written the header. Okay, so now I am going to write the code for depadding. Okay, so the code for depadding is very simple, right? So I'm going to go, I'm just going to write for so everything remains the same. Only thing is I have to write a small function to depad it. Okay, so I would say for so I would create another integer which is called position, so that I can track the position of the pixel, right? So what I'll do is I will go at the beginning and add one more integer called position. Okay, so unsigned int. Okay, and then I will call this as, or I can call it here as position. Okay, so this is going to be position. Okay, so what I'm going to do is for I, okay, so for unsigned int, okay, I equal to pad, So I'm going to just copy from location and I less than h minus pad, right? And I plus plus. Okay, and then I'm going to set the position of the pointer. Okay, will be equal to data offset plus I into width into 3. So they are red, blue and green pixel, right? Okay, plus, so the initial pad into 3. Okay, so in this case this will be called offset. Okay, so that would be my offset for the starting of the row, right? That will be the offset for the starting of the row, isn't it? Because the first two rows are covered by 3 into pad, right? Data offset plus width into 3, right? Width into 3. So I'm starting from the pad itself, right? So the first, because I'm starting from the pad, the first rows which are zeros will be gone, and then I have to remove the pads on the left hand side. So that is plus pad into 3. So that is the starting location of my reading. So I will say f seek position fp comma position comma 0. So that will be basically placing my file pointer where the data starts, and I will repeat this procedure for the width of the pixel, width of the row, or the width of the image. Unsigned int j equal to 0, j equal to 0, j less than width minus pad, right? J less than width minus pad. Okay, so I will run for j from pad to width minus pad, sorry, from pad to width minus pad. Okay, and j plus plus. Okay, so here I am just going to read the pixel and write the pixel. So I'm going to just say read f read the character, size of character, and one character at a time, and just say f write the same character back, character size of character comma 1 comma fw. So I have to do this for blue, green and red, right? So I will just take this Control C, Control V and Control V. So I have written the image data. Okay, and then I close the image. So once I have run with the depadding, I'm going to just generate the prototype of this. So I'll just copy this one, Control C, and then I'm going to go to the header and say Control V, and here I'm going to remove these names which are not required for the function declaration in the header. Okay, so we have done with the function declaration. Now I'm ready to run it. So I have padded the image and my image is in, so I am going to do a depadding, right, of the same image. Right, so I'm going to say this is going to be the path, which is going to be pad path, because I padded the image path first and then I'm going to depad it. Pad path, then I'm going to say depad path, which I haven't created yet, and I am going to depad by the same amount with which I have padded. Right, so this would be a legal function call. All I have to do is I have to put the depadded path. So in this case I will just copy this. over here and say depad path, right? And this will be called depadded. Okay, so now I'm doing two things. I'm padding the image first with 50 and depadding with 50, so I will get the original image. So if I build the solution, done, and then I'm going to debug it. So let me make this folder to be empty, right? So I'm going to take the same Lena image, first pad it and then depad it. Okay, so I'm going to say debug, start without debugging, and it's done. So let's see the output image. So that's the padded one, that's the depadded one. Okay, so this is the depadded one, this is the padded one, and then let's look at the original one. So original one over here, and original and depadded are the same. Now if you want to really see whether they are same, you can go here and look at its size. It's 768, right? If you do properties, okay, so it will be 786,486. Okay, so this is the depadded one. Okay, so now 786,486. So now if you find its properties, it is 786,486, right? So now the original image is the same as the depadded image. So now we have padded and depadded. So we are ready now for writing the filters, right? So to write the filters, what do you have to do? So here I'm going to put a 2 because I want to run a 3x3 filter, right? So I am going to write a program for filtering. So this is depadding. So I am going to write a program for filtering. Okay. Okay. So here I'm going to feed in these kernels. So if you remember, this is going to be your averaging, Laplacian, Robert, Sobel, Prewitt. All this I'm gonna do this in the filter, right? So I am going to write another function which is called flt 3x3. So I'm doing a 3x3 kernel. So flt 3 cross 3. Okay, so what is it going to do? It's going to receive the input file, right? Then it is going to write to the output file. So you need a write path, and then you need another string which is going to tell what kind of filtering you want to do. So I will call this as type. Okay, sorry about this. So now I am ready to do the filtering. So for filtering, what I'll do is I'll declare the kernels, right? And I will write to wpath as one output. In case of Sobel and Prewitt, I'm going to have the second one also. So for that I have to generate a second path, right? So this is going to be very simple. Okay, so all you have to do is, here I'm not dealing with files at all because I'm not doing convolution here. For convolution I'm going to write a separate function. So all I have to do is I have to fill the kernel, unsigned character, right? Should the kernel be unsigned? No, it should be character, because the kernel can be, kernel can be a negative number, right? So I'll say character, KERN, okay, H. So for horizontal it will be a 3x3 matrix, correct? Then I'm going to have kernel for V, which is vertical, right? This is again 3x3. Then I'm going to have another kernel which is going to be 2 by 2. So I'm going to have KERN 2 by 2. Okay, so I have done the initial work. Then I'm going to create the path for the filt2. So I might or might not use that depending on what kind of filtering I'm doing. So I'll say FLT path 2. Okay, and then I'm going to write it to the output folder. So I am going to just copy that, Control C, Control V. Okay, so this would be called filtered2. Filtered2. Okay, so this is only in the case of Sobel and Prewitt. Now the next thing is I'm going to fill these kernels. So if okay, string comparison, so I have to include string.h. okay, it's there. If not, so if the string compares, it returns 0, right? If not, strcmp. If not strcmp, and I'm going to compare type. Okay, and the type I'm going to say is, does it match to something called Sobel, right? And then I'm going to fill that kernel. So there are going to be 2 kernels which I have to fill, the horizontal and the vertical. Okay, so I'm going to say, I'm just going to type it, KERN underscore H 0 0. Okay, so for Sobel, what do you have? Okay, for Sobel you have got -1, -1, -2, -1, right, as the first column, right? So that's what I'm going to do, -1, so that's there. Then you have got -2, then you have got -1, right? And then you have got all of them as zeros, right? So you have all of them as zeros. Okay, so all the column, second column is entirely 0. Okay, second column is entirely 0. So this is going to be 0 1 1 1 and 2 1, right? And the third column is going to be the same. Okay, so the third column is going to be the same. Okay, so this is going to be your kernel for the gradient along the width. Now what about the gradient along the height? So I am going to just copy this, Control C, Control V, and instead of this I'm going to have V. So the V is going to be -1 0. So V. So the next one would be -1 0 1. Right. So the next one is going to be V, and V. The second column is going to be -2 0 and 2. Correct. And the third one is again V, and V. And these numbers are going to be -1 0, -1 0 and 1. Okay, so this is going to be -1 0 1, -2 0 2, -1 0 1. So this is going to be the vertical kernel. Okay, so now I can do the same stuff. So in between I'm going to call, right? So I'm going to do this with Prewitt. Okay, so I'm going to say if this is equal to Prewitt, Okay, so if this is equal to Prewitt, Prewitt. So in this case, it's going to be -1, and -1, 0, 0, 0, and then 1, 1, 1. Hang on here. -1, -2, -1, and this should be 1, 2, and 1. Right, so and this one would be 1, 1, and 1. Okay, so it will be this. Okay, and then vertical kernel would be -2, -1, minus this thing, and 0, 1, 1, 1. Okay, so we are set with the kernel, right, for Prewitt. The next thing is going to be robot, right? So let's do averaging first. So if the next one is AVG, so I'm averaging. Okay, AVG. Okay, and okay, so here I have to, okay, I have to do averaging, means everything is going to be 1, and I don't require 2 of them. So I will just, with the horizontal kernel, I'll be okay, and everything would be 1 here. Right, so everything is a 1 here for averaging out. So kernel H in this case is filled with 1s. Okay, so I'm done with that. Then Laplacian and high pass. So I am just going to copy this one, and I will call this as Laplacian. Laplacian. So Laplacian I'm going to fill with first column as 0, 1, 0. 0, 1, 0. 0, -1, 0, sorry. And then I'm going to have -1, -1, 4, -1, 4, -1. This is the second column, right? And the third one is going to be 0, -1, and 0. Okay, so I have filled the Laplacian kernel. So let's do a high pass. Okay, so I will call this as HPF, right? Control C, Control V. Okay, so this will be called a HPF. Okay, and HPF would be everything -1. So first column is all -1. Second column is -1, 8, and 1, -1. And the final column is -1, -1, and -1. So this will be the high pass, right? Now I have to do the robot, right, and median. So median, there is no kernel, right? So I will just put here Control C, Control V, and here it is going to be Robert. Okay, so in case of Robert, I don't have this, right, and I don't have this. Okay, and I don't have this. Okay, so we fill in the Robert filter, which is going to be 4 elements. So this is going to be my first column, 0, 0, 1, 0, and that is going to be -1 and 0, right? And then it will be 0 and 1. So this first column is -1 and 0, and the second column is going to be 0, 1. Okay, so that's going to be your Robert filter. Okay, so next is I'm going to have something called a median filter. So if strcomp right type with what is called median, then it's going to do the median. So it's going to call some function. Okay, fine. So now we are done with this. Then we are going to write convolution, right? So for convolution, I can write another algorithm called conv. So here you see I haven't opened any file, though I have passed two strings referring to the input and output file, and there may be a third output file. There may be a second output file, because in case of Sobel and Prewitt, you have to have two kernels, right? One for the horizontal, other for the vertical. Okay, so now what we are going to do is we are going to write a function for convolving, right? So I am going to say void conv convolve, and to this I'm going to pass, just 1 second. Okay, to this I'm going to pass the file path. So that's going to be a string that will be called the f path, right? F path, and then there is going to be a write path that will be w path, correct? And then I am going to receive a filter. So unsigned filter kernel, right? And it will not be unsigned, it will be just a character, sorry. So this will be a character, which can be a negative also, right? Because kernel values can be negative. Then I can say FLT, sorry, 3 cross 3. Okay, let's give it a different name, because that's called a function, right? So it will be trying to call a function. FL3 cross 3, how's that? That's fine. So I'm going to receive a string of that, or a matrix, right, for that with that filter coefficients, and then I'm going to have a boolean which says, do I want to normalize it, right? So that's the thing. And then I'm going to have an unsigned character for reading, right? Call it ch. Then I'm going to have unsigned int that's going to store the position of the pointer. Okay, so there will be two of them. Then I'm going to have unsigned int to control the to receive the offset of the image and the width and the height, right? And then I'm going to have unsigned int to store the summation of the dot products, right? So that will be b sum for blue image, g sum for green image, and r sum for the red image, correct? And then I'm going to have two file pointers. One is for the input file, which is going to be fp, other is for the output file, which is fw, right? So once I have that, then I can just open the file. Fp is equal to fopen, okay, that file which is pointed by fpath, right, comma, in a write binary mode, or in read binary mode, sorry. And if that succeeds, then if fp is equal to null, then I'm going to return a statement to myself reminding that it failed to open the input file. Fail to open the input file. Okay, and then I'm going to go ahead and just return this from this function. So it has done nothing, but it has just given me a warning. But if it opens, for example, then I'm going to start the processing. Okay. Okay, so if it opens, the next thing I'm going to do is I'm going to try to open the output file, right? So the first statement will be fw, right? Open the output file, right? Fw fopen. Okay, w path, comma, write binary mode. So I trying to open the sorry. So I'm opening the write file, and then I'm checking if it is null. So then I'm checking if it is null. So if fw equal to null, then I'm going to just return. I'll print a message to myself. Failed to open the output file, new line, and then I'm going to say f close the open read file, which is fp. Then I'm going to say return. Okay, so if this happens, still I'm going to return without any information. Else I'm ready to process it. Okay, so first thing is I'm going to read the extent of the files, right? So I will say fseek fp at the 10th byte from the starting, read the integer which stores offset. So I have read the offset. Then I can read the width and the height of the image. So I can say fseek, which is at the 18th byte, reading the width, size of an integer, okay, size of an integer, fp, sorry, fseek, I'm writing, sorry, fseek fp at the 18th location, fp at the 18th location from the start, sorry about that. And then I have got fread. From that 18th location, I'm going to read the width of the image, right? And then again, the next integer which is pointed by the file pointer is going to be the height of the file. Okay, so now I have read all of them. Then I'm going to place the pointer to the start of the read file, right? So I'm going to say fseek, then I'm going to say fp, place it at the start of the file. Now I'm going to copy the header of the file as is. So I'm going to say for unsigned int I is equal to 0, I less than offset I plus plus. So here I'm going to just read the byte by byte. Right, I'm going to read the byte by byte from this, and I'm also going to write byte by byte from this file. fw. Okay, so we have copied the header up to this point. Now we are ready to process the convolution, right? So for the first one, for the first what you call first row, okay, we don't do any processing, isn't it? So that is anyway 0, right, for red, blue, green. So I'm going to read and write that as is for so I have to do this with though the pixel is black, I have to copy this 3 times, right? So the first one is red. So then I'm going to run for height minus 1, right? So I'm going to run a for loop okay. So what am I going to do for this reading? Okay, the the first one, because this is a 3, right? I'm not assuming 5. So for the 3, the first one would be a black character or black pixel. So anyways, I'm going to waste that read and write as is. So I'm going to waste that read and write as is. Correct? So this is what I have done. Now the real action starts of convolution, right? So I'm going to say for unsigned int j equal to 0 and j less than width minus 1. Sorry, width minus 1 j plus plus, right? So here I have placed I will place the position of the pointer, file pointer, right? So position would be equal to, at the beginning of the row, offset plus I minus 1. Okay, so one more thing I want to say is, see, I have written the first one already here, right? So I will start from 1, right? So I have written the first row anyways, and here also I have written the first pixel anyways, right? So I will start from here, right? And this one I'm going to place, right? So this one I'm going to place right at the start. So this is the corner of that matrix, right? W into 3, right? Plus and j minus 1, right? J minus 1 times of 3. 3 because there are 3 colors, right? That's why. So let's see what happened. So I have got position at the start of the row. Every row which is pointed by I, right? Its initial position will be I minus 1 into W into 3 plus J. So J would be along the width. So I'll be moving the entire kernel along the width of the file. So that is why I have J. So J minus 1 into 3. So that will be the pointer. So I'm going to initiate B sum is 0 because I'm going to take the dot multiplication, so member wise multiplication of the 3 by 3 matrix with the kernel, right? So I'm going to say B sum is equal to 0, G sum is equal to 0, and I have R sum equal to 0, right? So once you are done with this, you are going to do it for 3 times, right? 3 times multiplication, right? So basically 3 into 3, right? Okay, so I have to run 3 cross 3. So for, I can say unsigned int, okay, k is equal to 0, k less than 3, k plus plus. So this is the matrix, right? So once I've done with this k, I'm going to find out the position of position will be equal to POS plus k times of W into 3. So that's basically the corner, or rather this is the mid value, not the corner, right? So this is pointing at the mid value. So k goes from 0 to 3, right? So position, so k equal to 0, that means it's going from the corner, right? So that's the corner. Okay, then I'm going to say fseek fp at position 2 from the starting of the file, right? And then I'm going to have for L for the column, right? Unsigned int L equal to 0, L less than 3, and L plus plus, right? So now here the inner product would be done for the kernel and the what you call kernel and the matrix of the image. Okay, so I'm going to say fread, and I'm going to read it in a character from the file. So I say size of character comma 1 comma fp. So I'm reading the first pixel in that 3 by 3. Okay, and I'm going to say bsum is equal to bsum is equal to bsum plus ch, right, times of something, which is going to be the content of pointed by this pointer, which is going to be fl 3 cross 3. Okay, fl 3 cross 3 plus k times of 3 plus L, right? And then I'm going to read the next character, right? So I'm going to read the next character and store the summation in the gsum. So the next character has to do with the gsum, correct? And the next character would have to do with the rsum. Okay, it's the same kernel value would be applied. So once I'm out of this, okay, once I'm out of this, I have got okay, so once I'm out of this, I would have convolved the kernel with the entire image, isn't it? So bsum, gsum, and rsum are going to be there. Okay, now if this one is if div, okay, so div is a boolean, so if it is a averaging filter, then it has to be normalized to 9, right? So I would say ch is equal to bsum by 9, right? So it is normalized, and then I'm going to write ch, right? So fwrite, hang on a second. Okay, so I'm still in this I cross h, right? Yeah, so I'm still convolving with the image. So f right ch size of character comma 1 comma fw, sorry. So I'm writing to the image. Then what do? I will do a gsum. So this is for your averaging filter, right? So I'm going to do gsum is equal to is written to the file, and then rsum is written to the file. Okay. Else, so in this case every number is going to be positive, so we are not worried about a negative number in in doing the mean or average, right? But okay, but we would be looking at, so if b sum is less than 0, okay, then I'm going to say b sum, okay, so if it's less than 0, then ch is equal to, let's say, 0. Else if b sum is greater than 255, so these numbers would arrive in some cases. Okay, so then ch is equal to 255, correct? So what's happening here? Else you have ch is equal to b sum, correct? And ch would be written to the file. So I can say f write okay, I've updated ch value. I'm going to write this 1 byte fw, correct? The same thing I will do with the gsum. And same thing I'm going to do with the rsum. Okay, and I have written to the file. Okay, so this is this if then else statement. Right, now I will come out of the row. So basically I'm out of this one over here. So here I have come out of the row processing, so I have to put the last pixel. So last pixel will be just a repetition of writing the zeros, right? So where did I do it? So over here, this one, right? Yeah, so this thing I'll do for the last one. So I have to be at this far level. So here I'll just write it. So I have written the last pixel. So once I have come out of this, I am out of the h. So I have run it for the height wise. Now I have to write one blank one blank line, which is over here. So this is all zeros, right? So this is the last row, right? Yeah, so it is be at this level. So I'm writing the last row. So once I have written the last row, then this is the end of the else, right? So before I finish else, I would have to do a flush fw, then I have to do fclose, fp, and then I have to do fclose, fw. Right, so this function basically is convolving whatever matrix is given or kernel is given, it is doing that convolution, right? So I'm ready for every 3 by 3, I'm ready here, right? So I have to do a prototype of this in the header, right? So, well, first of all, let's see if I have a filter prototype. So I have to write the filter prototype first. Okay, so this is the filter prototype. Control C, Control V, and all I need to do here is just the type which I'm passing. So this is for that, and then there is a function for convolution which I have written, which has a signature like this, right? So this is for conv. I'll put it in the header file as this prototype. So I'm passing the boolean to decide whether I'm normalizing it. I'm passing the kernel here. I'm passing the write path here, and I'm passing the read path here. So when this is done, so I should be going to write and look at this filter. So if you were to do this, okay, in this folder, then this should be declared above, right? So convolution should be kept in a separate file. That's what I feel. So if I do that, I do Control X from here, and instead of the header, instead of that, I put it under image stat. How's that? Okay, let's paste this here. Right, so it looks okay. So that's fine, and then this convolution will not be here. It will be in the header file of imstat. So it would be somewhere here. Correct. So we are all set. So the reason is that we have to have a sequence, right? So this function has to be declared before the filter is called, right? So if the filter is in here in C file, then once I have included the header here for the image write, okay, here image stat is already there, so that function declaration of convolution will come here before this function calls it. So to me, that's okay. So now all I need to do is I need to go to the filter and I need to apply, let's say, for averaging. Okay, so let's try with the averaging first. So I need to have a convolution, this call for convolution of the kernel with the image. So over here in averaging, I'm gonna call that. Okay, and to this I'm going to pass the f path, the write path, the kernel. So in this case, the kernel which I'm going to call with is kern underscore h, and the boolean I'm going to do is true. So this has to average out. So basically, for averaging, this is the story. Then if it was a high pass, right, or a Laplacian, then again there is only one kernel, right? So I can call this convolve from within that if statement for Laplacian, right? Let's see that. Okay, fine. So I will be able to call this function for the high pass filtering also. So I can say copy for Laplacian also, because it's only single kernel, right? So but here I don't want to normalize this to 9, right? So this will be false, correct? So this is for Laplacian. Same is true for the high pass also. Okay, so this is going to be false, right? Now with Robert I haven't implemented, and with median I haven't implemented. So this is a 3 by 3 convolution. For Prewitt there's going to be 3 calls. Okay, 2 calls, sorry, to this function. So I'm going to call this one with the horizontal kernel. So that would be over here. Okay, so that will be the convolution. But for the vertical one, the call would go to not to W path but to FLT path 2. Okay, so in Prewitt it will be writing a second file. Control C, right, and Control V. Okay, field path 2. Okay, so that I will be passing in Prewitt, and this would be the vertical one. Okay, so with that I'm done with the Prewitt filter. How about the Sobel one? For Sobel again there are 2 kernels. So one would be this one, copy, paste, and the other one would be this one, Control C, Control V. Okay, so all 3 by 3 matrices kernels would be called, other than Robert and median. Robert is 2 by 2 and median is going to not receive any kernel, right? So we are ready to experiment with this. Okay, so I will go to bmp.c. So I will pad it with 2. Then I am going to call the filter. Okay, so that would be that one. Okay, so this will be the filter call. Control C, Control V. So in this case, okay, my input file will be the pad path. So this will be the padded image. Pad. And my output image, I'll create something similar. So let me go to filter. So this will be the output image, filter path 2, filter 2, right? Filtered 1 and filtered 2. Okay, so filter path 2, no, filter path 1, this will be filtered 1. So this is where the width wise I'm convolving the width wise, so this will be filtered 1. Okay, so filtered 1, correct? Okay, and then let's say I want to do averaging. That's the simplest one I can pick up, correct? And we are done with this. So now the filtered image, the padded, first of all the input image will be padded by 2 pixels. Then the padded image will be filtered to filter 1, and it's only filter 1 only. And then I have to depad the filter 1. So I have to depad the filter 1. and that would be under depad path, right, by 2. So here I am ready to run it. So first of all, I am going to build it. So seems like I have a lot of problems here. Okay, let's solve one by one. First of all, f flush undefined. So this is f flush, not ff flush. F flush. So that's correct, huh? FLUSH, sorry. Okay, so this is corrected. What's the other thing? Convolve had different levels of indications for character 3. So these are warnings. Okay, usually that happens. Okay, let's build this again. Build solution. What happened? Oh, did it build? Okay, it did build. Okay, so now we have to decide the input image. Okay, so let's look at our images. Okay, so here what this averaging will do, for example, there is a noise, which is a white noise here, you can see here, right? There's a white noise here. I want to minimize this, so I'm going to do a averaging, or let's say this one, rows. Okay, so here you will see also the noise is there, right? So everywhere this noise is there. Okay, so I want to minimize that noise, right? Though it will blur it, but will get rid of that noise. So here I'm going to remove this one from the output, and I'm going to feed rows.bmp as the input. Rows. Okay, so rows will go into here. It will put a padded path of 2. Then it will call with the pad path, it is going to write filtered 1 with averaging, and then filtered 1 will be depadded to depad, right? So that's what's going to happen. So I'm going to build solution. I think this is done, and then I'm going to say debug, start without debugging. Now if I have done some blunder somewhere, I won't have the results. So it's going to take some time because it is doing that kernel convolution. So I'm not sure what's doing. Let's wait for it. Should come up with some answer. So let's see what images do I have. So I got the padded one. I don't have the filtered one yet. So unless this finishes, I cannot have the filtered one. So the padded one looks okay to me. Okay, so where were we? Okay, so so what we're going to do is, I don't know what happened. Okay, so we are running with rows.bmp. We padded the image by 2, and then we send it to the filtering, and then the result of filtering we depadded. So it exited with code 0. That means everything is okay. And what I'm going to check is whether I got the output. So in my folder I got 3 pictures. So padded is this one, right? And the input is this one. Okay, so now this is the input image and it is the padded image, correct? Let me see if I'm recording. Okay, so this is the input image and this is the padded image. So you can see both are the same, right? But it's just there is a there are 2 pixel wide black line around it, so it's a padded one. The next thing I'm going to do is let's look at the filtered one. So this is the filtered image. Okay, so the filtered is going to still have the padding around it, right? But now you can see that all those noise basically has blurred out here. So this is what averaging will do. It'll blur the picture, right? So it has blurred the picture and there are no such grainy noise is not there, right? So if you magnify this, for example, let's say zoom this in, you see the grainy nature of the picture here. And let's zoom that one also. Okay, so this one on the right is not so much grainy as compared to the one on the left, isn't it? Right, so you see this portion, you see all the noise over here, the noise over here, the noise is over here blurred out. Right, so this is what averaging will do. Right, so let's look at some other kernels also. So I'm going to get rid of the output here, close this out, close this one out. So let's look at the high pass filtering of let's say Lena image. So I'll put here Lena, right, and here I am going to do a high pass filtering, HPF. Right, so from here on I will compare the depadded one with the original, right? So I'm gonna say build solution. I think we have already done that. Okay, and then I'm gonna say start without debugging. So it has exited with code 0. Let's go to the output folder. Okay, so I have a depadded one here, a filtered one here. So filtered one is depadded. This is a padded one, right? So let me compare the depadded one with this one, original one. So this is the original, correct? And this is the depadded, right? So what did it do? It did a high pass filtering, right? So what you are going to see is any changes in the color, they are going to be highlighted here, right? So that's a high pass image. Okay, so let's run on this Laplacian. Okay, so let's get rid of this. Let's run on this Laplacian. So HPF Laplacian, Laplacian. Okay, so Laplacian, build solution, done, and the output is empty. So say debug. So Laplacian will be similar to high pass, right? Done. So here depadded. So this is the result of Laplacian on a image, right? Now let's do a Sobel, right, for the edge detection, right? So I want to detect the edges. So this is a high pass filtering here, right? So let's run a Sobel here. So what I'm going to do is I am going to run a Sobel here. Sorry. Okay, so I'm going to have two filtered images, filtered 1 and filtered 2. So basically I will have to depad 2 images, right? So filter 2 and I have to go depad it 2, right? No, I have to just depad it. So filter 2 is not depadded here, right? Hang on. Where will I apply depadding in this case? So I'm going to write to calling this over here. This is going to write. I can call a depad over here for filter 2, right? Control C, Control V. So I have to take a filter 2 and I have to write to depad 2, right? So might have to get that thing over here. That's okay. So that's going to do a depad 2. Okay, so now let's build it. That's okay, doesn't matter. Okay, without debugging. Okay, it exited with code 0. Let's go here. Okay, so you have got depadded and depadded 2 as the result. Okay, here this is from filter 1, which is running widthwise, and this is from filter 2, which is running height-wise, right? And this is going to be the input file, which is this one, right? So you have, in one case you are looking at the edges on width-wise, you are looking at the edges, and then the height-wise you are looking at the edges. So that is what a Sobel is doing. So let's take another sample image, because here I could not get the get the right one. So let's look at which image is suitable for this edge detection. Okay, how about this one? Or let's say much simpler than this. Okay, maybe I'll run on this one. This is child.bmp. Build solution. Debug, start without debugging. So this is a large picture because 180 by 1080 by 1080 is the size of the picture. It's almost 4 times in size. So it's going to take some time. But this is what is happening with the Sobel filter. So it's almost 4 times the picture size. Let me see if I'm recording. Yeah. Come on. Okay, so it exited with code 0. Let's go to the output folder and see what happened here. Okay, so depadded 1. This is going to be the edges going from left to right, right? And let's look at depadded 2. This is for the edges going from top to bottom. So can you see that you have got lines here? So you have got lines here which are going to be horizontal because I'm coming from top to bottom. So the edges, all the edges which are from top to bottom, they are detected, right? Now if you see the other one, the lines are going to be vertical because I'm going widthwise. I'm going from left to right. In the other one I was going from top to bottom, right? See, another one I was going top to bottom. So you can see that for this picture, sorry about that. So we have got the edges vertical as well as the horizontal edges. Okay. We have got the vertical as well as horizontal edges which are detected here. Right. So this is going to be with the Sobel filter. So let's see what happens with the Prewitt filter. Prewitt filter, right? Okay, so let's see what happens with the Prewitt filter. Prewitt. I think that's how I named it. Let's see. That's the Prewitt filter, and I have to do the depadding everything over here, right? So I'll just copy these lines under Prewitt. Prewitt. Fine. Okay, so I'm going to build solution on the same image. Let's go to a different image because that's a big image, right? So I don't want to use a big image. How about going back to Lena? Right. And debug. So okay, I don't know what it did. Could not start. I don't understand why it could not start. Prewitt. Why can't it do that? Build solution. Debug. Okay. So this is a 512 by 512 image. So that's not as big as 1080 by 1080. Okay, the things could have been faster if I had written it in a matrix, but I am reading from a file. I am writing back to the file almost 4 times or 5 times here. Okay, it's done. So let's go here. So this is Lena. This is a padded one. So I can look at a depadded one, but it's okay. And then this is filter along the width. So all the vertical edges would be detected. And this is along the height. All the horizontal edges would be detected. Correct? So this is the filtering, the edge detection part of it. Okay, so now I have to do this with robot and median. Okay, so I'm going to just modify the path for convolution for a 2 by 2, right? So the robot filter is over here. This is a very small kernel, right? So I will go to image stat. I will copy this one, Control C, Control V, and I'm doing the same stuff. It's just that I am going to be supplied with a kernel Okay, so I will call this as convolution 2, and I am going to pass this FL2 cross 2. Right, so once I get FL2 cross 2, then up to this point, okay, there is no information, so I can just make it 2 and make this one 2, and does the position have K and L index? No. K index, yes, but not the this one. Let me try to understand. Okay, so this will be a 2 cross 2. 2 cross 2, sorry. 2 cross 2. And 2 cross 2. Okay, so this is with the robot. 2 cross 2. And there is no question of averaging, right? Because this, we are very clear, there is no averaging here. Right. So there is no question of if here, if div. Okay, so basically I can do a control X on this. Control X. And this if statement would be gone. We'll be directly working with this. Right. Okay, so that's done. So 2 cross 2. And this is less than 2, and this one has to be less than 2. Less than 2, L less than 2. So this is a 2 by 2, FL2. Okay, so this is a convolution 2. So there is nothing special about this. All I have to do is create a prototype of this one. Copy and put it in the header file here as a convolution 2. And this is going to receive the kernel here, the write path here, and the read path here. Right, this is done. Okay, so in case of here, when it comes to robot, I am going to call convolution 2. Convolution 2 I'm going to call, but without this boolean. Convolution 2. Make sense? So this will be applying a 2 cross 2. And it will be doing edges which are kind of diagonal, right? So this is a robot filter. So let's try this robot here. R-O-B-E-R-T. Robot. And that's what I named here, right? R-O-B-E-R-T, right? So I think I'm all set. So I'll build the solution. Okay, and then I'm going to debug it. So exited with code 0. That means everything succeeded here, and I'm going to go here and look at the output. So why? Okay, of course, you know, there are 2 of them. So I'm going to just delete them and run it again. Debug, start without debugging. There is no second filter 2 because this convolution is only along width, or you can say along height is the same thing, right? So it is already done. So now you have got the original image and the robot filtered image. So let's look at the depadded one. Okay, so here the edges which are diagonal, they are kind of enhanced, right? So this is the result with the robot filter. Now what remains is the median filtering, right? Okay, so in median what I'm going to do is I'm not going to have any multiplication, right? I have to do a convolution 3. So everything remains the same as convolution. Convolution is just that I am going to change, I'm going to do sorting. Okay, so let's do a sorting to find the median, right? So I'm going to just copy this and I'm going to just paste it here. And I'm going to call this as a convolution 3. Okay, so this will be doing the median filtering. And there is no division by 9, so there is no boolean. And here I am going to get rid of this section. Control X and this if then else statement. Okay, and when I'm doing median, really I don't need even this one. Okay, I can just say I don't have to verify if it exceeds the range, right? So basically I just do this, that I write directly. Okay, gsum and rsum. Okay, so this is straightforward. Okay, now let's see the sorting part of it. Okay, in median filter I take the 9 pixels, right, and I'm just going to sort them out and then find out the mid value, and I'm going to just write that mid value. So that would be called the median filtering. Okay, so just bear with me a second. So okay, so all I got to do is when I reach here. Okay, so in median filtering I need to create a matrix which is for blue, green and red, in which I'm going to read the results. Okay, so in median filtering I have to create blue, green and red rather than this sum. So I'm going to create blue, green and red, and this is going to be a matrix of size 9 because there's going to be 9 pixels which I'm going to read per color. Right, so the remaining path is the same until I reach here, and I copy the header up to here. It will be the same, and here I need not even pad it. Yeah, but that's okay. Okay, so here it's going to be the same. It's going to be the same, the first row and the first pixel value. First row and the first pixel value. That's perfectly fine. Then I have got first pixel value, then I have got J, right? Then my position is here, right? And then this is gone. This initialization is gone. Then I place the pointer. I place the file pointer at appropriate location, and I'm just going to read it. Right? So I am going to read and write it. Okay, so f read, and then this portions would be different. So this is blue, green, and red. So this I will put it into the matrix, which will be a blue matrix, and I can say k into 3 plus L. That's fine, right? So instead of indexing, I'm going to use a linear indexing. So I converted it to vector, right? And same thing is going to do with the Control C, Control V. Same thing I'm going to do with the green, and same thing I'm going to go do with the red. So I fill the matrices first. Okay, so once the matrix is filled at the end of it, right? Once the matrix is filled, then I'm going to sort it and then write it. So I have to do the sorting part. Okay, so sorting part is very simple. So I have filled the 3 by 3 matrix here, right? Then I'm going to sort it for, and this is just a linear sorting, right? Int I equals 0, I less than 9, I plus plus, right? So I'm going to sort out all at once. Okay, if something, if blue I, so of course this is for that, and then I have to run it from I to, so I want to do a bubble sort here. Int j equal to I plus 1, correct? Okay, j less than 9 and j plus plus, right? So at the end of this, I will have the blue, green, and red sorted out. So I will say if blue I, if blue, sorry about that, blue I is less than, sorry, blue I is less than blue j, blue j, then I'm going to swap it, right? Okay, so I have to create some more characters which will store the temporary location, right? Min b, min g, and min r. So let's go here under character. Min b, min g, min r. That's perfectly fine. So to do the sorting, if this happens, then min b is equal to blue I. So I'm just swapping it. Okay, and blue I is equal to blue j, right? And blue j is equal to b min. Min b, sorry. Okay, so I have swapped. right? And same thing I'm going to do with the green. So this is like a bubble sort, right? Control C, Control V. If green eye is less than green J, then min G, I didn't need three variables, but it's okay. Min G is equal to green eye is equal to green J, and green J is equal to min G, correct? And then I have to do the same thing with red. So red eye is equal to red J is less than red J. Then min R is equal to red eye. And red eye is equal to red J. And red J is equal to min R. So I have swapped that. Now at the end, once I come out of it, I will say CH is equal to blue 4, which is the median value, and CH is equal to green 4, the median value, and CH is equal to red 4. Okay, so I have got the median values which I have written. Okay, so the remaining stuff remains the same for the file, correct? So this would be the median filtering, and in median filtering I don't even need this filter, right? So this filter is not there. All I need is two paths. One is for the read and other is for the write, right? So let me just create a prototype of that, right? Hang on a second. Okay, so let's create a prototype of this. Okay, let's see if I'm recording, which I am. Okay, so a prototype of convolution 3, that would be doing the median filtering. Control C. Let me save this. So everything looks okay to me. Go to its header. This is convolution 3, and I don't need this guy, and I don't need this guy. Okay, so once I've done with this, I will go to image write. Under filtering, under median, I am going to convolve 3. So that will be convolve 3, and here there is no information about a kernel. So this is going to do the median filtering. So let's try the median filtering on the rows, right? So let's first get rid of the outputs, right? And I want to do the median filtering on the rows, right? So I'll go here, I'll say rows, and on the rows I just want to do the median filter. Okay, so once this is done, so let's just build it, and let's just run it. Unless I goof up, it should be okay. So it exited with code 0, means it has successfully completed it. I'm going to look at the depadded one, and I'm going to look at the original one. Okay, so if I look at the depadded one, I am going to enlarge this. Sorry about that. Okay, and let's enlarge this image to see the grainy nature of the image. Let's see the filtered one, which is median filtered, right? Let's enlarge this one too. Okay, so the grainy nature has become the blurred nature. So if you see here, this portion and this portion, the grainy nature has become the blurred nature, but this is median filter, right? So whether this noise was a right noise to be using median filter, or there are some other filters we will check later on, right? So I'm going to stop here, right? So we have done in this exercise, we have done the low pass filtering, which is averaging. Then we have done high pass filtering, Laplacian filtering. Then we have done edge detection using Robert, Sobel, and Prewitt. Then we have done a median filtering, right? So we have done the neighborhood based processing for a filter. Okay, and also to be able to do that, we were padding the image and depadding the image, right? So what I'm going to do is I'm going to stop here and see you in the next exercise, where next session, where I'm going to talk about working with the in a frequency domain. I want to work with some of the techniques in frequency domain. So we will be doing FFT, DCT, and stuff like that, right? So thanks a lot. Thank you.